welcome to the video. So I'm going to talk about kind of two problems with this cylinder. So it is related to calculus, and the assumption is that you now know derivatives. Now, if you know derivatives, at least the first derivative, second derivative, and so on, you can apply it to many maximizing and minimizing problems. So let's take a look. Here I have the maximization volume of a cylinder on the assumption that the surface area has been given. So it's some area A. Now, sometimes maybe you're going to run into this problem where A might be an actual number, but here I want to keep everything in terms of variables, but the key thing is that the area is known. So that's going to be our first problem, maximizing volume. The second problem that I want to take is, again, taking a cylinder, but then now flipping it. Now, the volume is given, but now you want to minimize the surface area used for that volume. So let's take a look at these two particular problems and then how you can use calculus and particular derivatives to be able to solve it. Let's say without any tools now at all. So, no graphing or anything like that. All right, so let me come back to this. The first thing that I'm going to do is, because I want to maximize volume, I can see that my volume is dependent on two variables, on the radius and then the height. I don't want it to be dependent on two variables. I just want it to be dependent on one variable so that I can take a derivative with respect to that variable. Now, because the area is given right here, so I am assuming that I know what this is. So basically, it's some constant. If that's the case, then what you can do is you can isolate this particular equation or this particular formula for either R or for H. Now, I'm going to do it for H, and then what I will do is I'm going to substitute H back into here, and you will see that now my volume formula is just with respect to R. And then I can go ahead and use my derivatives. So let's do that. If I isolate for H, I'm going to get that A, so the surface area, minus, 2 pi R squared, divided by, and I guess this is going to be 2 pi R is going to be equal to H. So I'm going to take this and now substitute it back into my volume equation. So what do I get? So volume now is equal to pi R squared times all of this junk right here. So I'm going to multiply it, I guess, by all of this. Now, just to separate this out, okay, let's just put a little dot in there so you don't think that they're combined together. All right, so now let me just simplify. I'll do this in kind of fast-forward fashion, and you can double-check it for yourself. Now that we have the volume equation, now I can take the derivative with respect to R, because this is only dependent on R, because please remember that the area has been given to us. So if I do that, then my derivative, so the derivative here, my first derivative, is just going to be, so this is going to be A over 2 minus 3 pi R squared. That's my first derivative. And now, if you recall from finding local and local maximums and local minimums, if you set this derivative equal to 0, you know what that means is that what you're looking for is where the tangent is flat. And then what we want to be able to see, so now in this case, we're trying to maximize this. So we want to be able to see that wherever we find, wherever this R is, okay, since we're maximizing, we want to be able to see that it's concave down like this. Now, concave down, we know how to test that because that is our second derivative. So our second derivative at a point will tell us if it's concave up or concave down, unless it's an inflection point, right? But in this case, we want to be able to see, okay, if the second derivative is going to be less than 0 at that point, so we know that it's going to be a maximum. If it was greater than 0, then it's going to be a minimum, right? Because then it's concave up. Now, first of all, let me just isolate this formula and let's see what we get. So we get -3. All right, so here is the answer. All right, so that's R. So that's where our derivative is equal to 0. And now let's check for the second derivative. So our second derivative, so I have to take this, take the second derivative. Well, that will not be very difficult because that's going to be just negative, I guess, 6 pi r. And now notice this r is positive. So if you would substitute it back into here, because of this negative, then obviously this is going to be less than 0, which indeed is exactly what we wanted. This indeed then is a maximum, okay, or at least a local maximum that we would have within there. So that's how you can utilize the derivatives to be able to see if your function, okay, in this case our volume that we're trying to optimize in some way, so find the maximum, just find the first derivative, isolate it, okay, wherever it is equal to 0, take the second derivative, and then once you have the second derivative, just check if it's concave up or concave down, and that just simply tells you what the sign of that second derivative is, okay? So that's the skills that we kind of have found in order to be able to see how this actually works. Now, you may ask, how do you know that this is the maximum? Because I know that this is a local maximum, but how do I know that on the range that I have that this indeed is the maximum? Well, this is the only place that I have found where the derivative is actually equal to 0. So the only other ones, so any critical points that I might have, okay, are most likely at the extremes where r is equal to 0, but then we don't even have a volume. And then the other one is, I guess, you know, you can think about what happens to h, right? So you're going to run into the problem that h is going to be 0 as well. So that maximum that you have in there, okay, so from the viewpoint of how we're graphing it, so this particular function, okay, it looks like it's going to run into some issues. And it's only going to have one point. So in this case, it's this point or this value for r where it is a maximum indeed. Now, whenever in doubt, you can also graph this. So you can pull up Desmos, for instance, graph the function, and then see for yourself, like how did that actually look like, and it is the maximum or not. Now, I am pretty confident, okay, in this strategy, so I'm going to leave it as it is for the moment, and then maybe we'll use a graphing for the second example, okay, so which is going to be coming up. Now, if you're trying to maximize this volume, you obviously would have to substitute this back in to the volume formula, so into here, to see what that volume would be at that point. But I'm going to leave that with you. That's just a matter of substitution. And then there is your volume. If somebody gives you the value of the surface area, then obviously you can get a number out of it. But currently, we just know that area is given, but we don't know what it is, okay? If you want to know what the height was, again, you can substitute it into your height equation right here, and then find out what that height would be. It's not going to be very pretty because we don't know, okay, again, what area actually is. We just know that it's fixed. But the strategy always is you find the first derivative, set it to 0, find your critical points, so basically where that tangent is going to be flat, and that's going to be either a maximum or a minimum. And then to check if it is a maximum or minimum, take the second derivative, and now you want to check if it is concave up or concave down, okay, to confirm for yourself. Okay, so let's use that strategy once again for this example. So in this example, we want to be able to see if we can minimize the surface area. Now, because we're minimizing, that actually tells us that, you know, we're minimizing. We're going to try to see that our second derivative, once we get there, okay, is going to be concave up, right? So we wanted to see it to be positive in some particular way. So we'll see if that actually happens. So minimizing the surface area. So we are now trying to find this, and we are given the volume. So I'm going to do the same thing. I'm going to first isolate for h. So h is equal to volume divided by pi r squared. And now I'm going to substitute this back into my equation. So my surface area equation is equal to 2 pi r squared plus 2 pi r times volume over pi r squared as so. So let me just simplify this. There we have it. And now I can take the derivative. So if I take the derivative of this, so let's see what that gives me. That's 4 pi r minus 2v r squared. All right. Now I want to be able to set this to 0 to get a critical value. So to see where the derivative possibly is equal to 0. And then since again, we're minimizing, we're trying to see if at that particular point that we find, okay, this is going to be concave up. So then we're going to need a second derivative to confirm that for us. All right. So let's take a look, okay, at what happens. Now I'm just going to take this first and let me massage this particular equation a little bit, set it to 0, and then I'm going to isolate and solve for r. All right, so I'll do that next. All right, so there we have it. Okay, so that is our r. So very odd. And now if we want to see if this indeed is the minimization, so let's take a look. We would take our 4 pi r minus 2v over r squared, so our a prime, and now we are going to try to find, okay, the second derivative. Okay, so let me do that and then I'll be right back. All right, so there we have it. So this, okay, so clearly this is positive, right? Now my r right here, so notice if you substitute that in because it's cubed, so that means this root would be gone, and then v over 2 pi is also positive. So I have this whole thing is basically greater than 0, so I'm guaranteed that. So indeed, I have this concave up, and this looks like this is going to be the point, okay, where it's minimal. Now, how many of these values do we have? Well, we only have one solution within here. There's no other ones, so that must be the absolute minimum that we have. Again, the extremes, so r at 0 is not going to work for us at all because volume is not 0. So now with this, if you want to know what that area is, you can substitute it back into here. So I know it would be a little painful because you would have to substitute it right in there and then find out exactly what the minimum area would be. So, you know, I can leave that with you as you substitute that in here. It's not going to be very pretty, but we know where it happens. If you want to know what the h is, then just substitute for r into here and then find out what h would be. Now, I said, you know, we can use a graph as well to be able to see and confirm for us. So let's pop up Desmos. Now, here in Desmos, let me just punch this whole thing in. So, you know, let's say a, and I guess a is going to be dependent on r, is equal to, and this was 2 pi r squared plus 2v over r. Now v, we have v as just some constant, right? I mean, in Desmos, we actually have to set it to a particular value. Now, it doesn't matter what it is. Okay, so, you know, here it's 1. And notice, okay, so, I mean, we're looking on the positive side, and it looks like, there you go, that is the minimum that we would find. So, for volume is equal to 1, so let's see, my r was, let me take out, so I'm going to just use, this is the cubed root, and this is v over 2 pi, all right? So that's what we found. That's where r is, right? So your y-axis is your area. So that's the area that we have. So notice it would blow up on us. Okay, if we go to the left or to the right, the smallest surface area we have is at this point, and that is that r is equal to the third root of the volume divided by 2 pi, which indeed, if you're looking there on decimals on the left-hand side and on the plot, okay, they are both equivalent to each other. And notice the second value, so the y value on the plot, the one that you see there, 5.536, at least for volume is equal to 1, would be your actual surface area. So that's the minimum surface area that you would have. Now, on a test, you're not going to be utilizing decimals unless sometimes your teachers allow you to use some tools. Okay, and if you're not, then you're going to have to use the first and second derivatives to be able to find these things. But if you're using graphs, you don't need the derivatives. You can just plot it, and then you can actually see what the answers would be. Now, the nice thing is, on the left-hand side, I did everything algebraically. I didn't set v equal to anything. It was just v, and then I was just solving my equations, taking derivatives, checking if it's concave up, concave down, and then I solved my problems. So this now is the encompassing of the first and second derivatives, and then how you can use it for some optimization problems, which I'm sure you're going to be running into calculus at some point. All right. Thanks for watching. Okay, happy studying your first crack at calculus and some applications. Bye, everybody. Take care.